Hey everyone, welcome to this explainer. Think of this as your ultimate interactive study guide for mastering number-based conversions. If you're a computer science beginner or honestly just looking to brush up on the basics, you are in the exact right place. Today, we're going to completely demystify how computers actually speak, count, and translate information behind the scenes. We'll be bouncing between base 10, base 2, and base 16 like absolute pros. I am so excited to walk you through this because once you see the patterns we're about to cover, you will literally never look at a line of code the same way again. Let's get into it.
Okay, real quick, here is our game plan so you know exactly what we're tackling today. We've got 1. The 3 number bases, 2. The power of the nibble, 3. Decoding letters A through F, 4. Some hands-on practice converting hex to binary, 5. Verifying our math with base 10, and finally, number 6, the final hex challenge. All right, Section 1, the 3 number bases.
So, to really get this, we have to understand the fundamental difference between how we count and how computers count. Our standard everyday decimal system, the one we use to count money or keep track of our age, is base 10. It gives us exactly 10 numbers to work with, 0 through 9. But the hexadecimal system, which is everywhere in computer engineering, is base 16. That means it gives us 16 totally distinct values for a single-digit space. It uses 0 through 9 plus the letters A through F. And this is a real game changer because it allows computers to store a massive amount of information in an incredibly tiny physical space.
Moving on to Section 2, the power of the nibble.
To actually translate between human numbers and computer numbers without getting completely lost, we need a secret weapon. And honestly, it has kind of a hilarious name. It's called a nibble. A nibble is exactly 4 bits, which is half of a byte. It's absolutely crucial because it's our master key for conversions. Why 4 bits? Well, a 4-bit sequence of binary zeros and ones can hold exactly 16 possible values, from 0 all the way to 15. That maps flawlessly to our base 16 hexadecimal system. So one single hex digit translates perfectly to one 4-bit nibble.
Okay, picture a little mini waiting line with 4 open slots. This is our conversion table. From left to right, these slots represent the decimal values 8, 4, 2, and 1. If you max out the line and add 8 plus 4 plus 2 plus 1, you get 15. Throw in 0 as an option and boom, that is 16 total possibilities. We are going to rely heavily on this exact mini 8, 4, 2, 1 line for basically every conversion we do today.
Section 3. Decoding letters A through F.
Now, you might be wondering, how on earth do we put a number larger than 9 inside a single-digit space? You literally can't cram a 10 or a 15 into one slot. That's exactly why we use letters A through F. You really want to commit this to memory right now. A is 10, B is 11, C is 12, D is 13, E is 14, and F is 15. Take a mental snapshot of this right now. From here on out, whenever you see a hex letter, your brain should automatically swap it for its base 10 number. It's the ultimate bridge between human math and computer hex.
All right, Section 4. Practice. Hex to binary.
Let's get our hands dirty and actually break these down into raw computer binary. It's a simple 3-step manual process. Step 1. Separate your hex digits so they're completely isolated. Step 2. Convert each individual digit into its own separate 4-bit nibble using that 8421 waiting line we just talked about. And step 3, just combine those resulting nibbles back together into one big string. Easy, right?
Let's try this on the hex number D5. First, we separate them. D is our first digit, 5 is our second. Now, D equals 13. To make 13 in our 8421 line, we need an 8, a 4, and a 1. So we put a 1 in those slots, giving us 1101. Okay, now for the 5. To make 5, we need a 4 and a 1. So that's 0101. Finally, we smash them together. D5 is perfectly translated to 11010101 in binary.
Real quick, I want to share a massive pro tip to save you from some really common mistakes students make on exams. First off, never read a hex number like 18 out loud as 18. In hex, that's actually one group of 16 plus 8 ones. It really equals 24 in decimal, so always say 18. Also, when you're converting your digits, never ever drop the leading zeros from a nibble if it's in the middle or right side of your final string. If you drop a 0 there, the whole entire sequence completely collapses.
Section 5. Verifying with base 10. So you've got this long binary sequence. How do you know for sure you didn't just mess up the math? We verify it by converting it back into our trusty base 10 decimal system. Let's look at hex A9. A is 10, which gives us 1010. 9 gives us 1001. So our combined binary is 10101001. Now if we map that across a full 8-bit decimal line, where the numbers keep doubling from right to left, like 1, 2, 4, 8, 16, 32, 64, 128, we just add up any column that has a 1 in it. We've got 128 plus 32 plus 8 plus 1, and that equals exactly 169.
And if you want to skip the binary step altogether to check your work, you can calculate the hex directly into decimal. Here's the proof. Take A9. The column on the right is the ones column, so 9 times 1 is 9. The column on the left is the 16s column. A is 10, right? So 10 times 16 is 160. Add 160 and 9, and bam, 169. The numbers align perfectly across all 3 base systems. No way you got that wrong.
All right, enough of me talking, it's your turn. Grab a piece of paper and pause this explainer right here. I want you to break down 7F into separate nibbles, convert it to binary, and then figure out what it equals in regular decimal numbers. Seriously, pause it and try it. I'll be right here.
Okay, let's see how you did. For the 7, you need a 4, a 2, and a 1. So that's 0, 1, 1, 1. And F? Well, F is 15, which means every single slot is full, 1, 1, 1, 1. Combine them, and you have a solid block of 7 ones. If you map that out and add 64, 32, 16, 8, 4, 2, and 1, you hit exactly 127. If you got that, absolutely fantastic job. Let's kick it up a notch. Let's try a 3-digit hex code, 3B7. Same drill. Pause the explainer, draw 3 separate little 8421 grids side by side, remember what number B stands for, and convert the whole thing to binary. Unpause when you're ready. Let's walk through it. The 3 is just a 2 and a 1, giving us 0011. B is 11, so we need an 8, a 2, and a 1, which maps to 1011. And the 7, like before, is 0111. String all 3 of those together, and you have successfully translated a complex 3-digit base 16 code into a raw 12-bit base 2 machine language. That is awesome. Section 6, the Final Hex Challenge. This is the ultimate test of what we've covered today. It's a massive 4-digit hex challenge, 1A5F. I want you to pause one last time, build your 4 nibble grids, turn the whole thing into binary, and then, here's the real test, write out a giant decimal conversion line, doubling the numbers from right to left, and calculate the final base 10 value. You've totally got this. Good luck.
All right, let's break down this absolute monster. The 1 gave us 0001. The A gave us 1010. The 5 gave us 0101, and the F gave us 1111. Now, because the very first 3 digits on the far left of our entire combined sequence are zeros, we can actually drop them. Remember, leading zeros on the far left don't change the total value. That leaves us with a beautifully long 13-bit string of 1s and 0s.
And for the grand finale, when you took that giant binary string, stretched it across a full base 10 table, going all the way up into the thousands, and added up those ones, you should have landed right on 6,751. Take a second to appreciate what you just did. You took a random 4-character code, manually translated it through raw computer hardware language, and calculated a quantity of almost 7,000.
Think about the sheer scale of that for a second. If just 4 little characters can hold a value over 6,000, imagine the staggering amount of hex processing happening behind your screen right at this very moment. Every single pixel, every color hue, every tiny memory address in the device you're watching this on relies on the exact base 16 and base 2 math you just mastered. You literally just learned the fundamental alphabet of modern computing. Thank you so much for hanging out with me today. Keep practicing those nibbles, and I'll catch you in the next explainer.